bit about me. I work on the Go team here in New York on static analysis tools, such as Vet and gopls and other things that power your IDE. And I'll be around all week, so come and talk to me if you want to chat about static analysis tools. I'm going to talk today about tools for modernizing Go code bases. First, I'll define and motivate the problem. Then I'll talk about two approaches to modernization that we're pursuing. Along the way, I'll show you what we've built and explain some of the challenges that we faced, and I'll wrap up with some plans and directions for the future. So one of the key value propositions of Go is compatibility. We're all familiar with the Go 1 compatibility promise that we will never make breaking changes, or as Ian Lance Taylor put it, Go to considered harmful. The promise means that old code continues to work indefinitely. Users can upgrade with confidence that the new toolchain and library are better than the old and not arbitrarily different. Yet Go itself continues to evolve compatibly. Each new release brings new features, affordances, conveniences, quality of life enhancements. And here I've listed a selection of language and library features that find use in nearly every Go file, or at least in every package. So just because you can leave old code alone doesn't mean you always want to. In an active code base, it's often worth modernizing the code to take advantage of newer, clearer, better ways to do things. Also, the extended forward compatibility feature of Go 121 makes it upgrading easy and transparent, so the whole ecosystem now tracks closer to the latest Go release. That means it's easier than ever to start using these newer and more convenient ways of writing Go code. So let's take a look at an example of a few of them. This program, and you don't need to worry about what it actually computes, is written in a style that was completely normal just a couple of years ago. But in recent years, there have been a number of changes to the language and the library that allow us to rewrite this function more simply. And these are the kinds of things that we would, I hope, all point out in a code review. Let's take a look at them in turn. The first thing is that we're trying to range over the lines of a file. Calling strings.split allocates an array whose size is the number of lines in the file. But it's completely unnecessary, since we're going to visit each element only once in order. And if we break out of the loop early, we did a whole bunch of wasted work. So Go 123 added a new feature called range over func, aka iterators. And the strings split seek function is like strings.split, but instead of computing the entire split eagerly, it returns an iterator that does it lazily, avoiding the allocation and avoiding unnecessary work. So let's make that change. We're not done. The next few lines, which loop over the fields, the space-separated words of each line, have essentially the same form as the new library function slices.contains. So we can rewrite the loop as a call to that function. And in fact, a variety of patterns of this form can be replaced by functions in the slices and maps package, such as slices delete, maps clone, maps copy, and so on. These allow us to eliminate many of these tedious little loops that Go is unfortunately somewhat infamous for. So let's make that change. This saved us 6 lines of code, and it also made it easier to read at a glance. Here's a third one. The 3-clause for loop can be simplified using the range over int feature from Go 122. So let's make that change too. OK, now we're actually done. So this is definitely an improvement in clarity. It also likely improves memory allocation and performance too, though you'd have to get a benchmark to really say for sure. But in general, the new features improve readability, consistency, remove distractions, and occasionally improve performance or address security issues. So what if we could automate this process? This would shift left the process of code review, saving time for both reviewers and authors. It would also have a second educational benefit. Not only does the code get better, but so does the developer, because they learn about new features of the language and library and then start to use them in new code. So that's one reason to build such a modernizer tool. But there's another reason. Let's talk about the elephant in the room, which is AI. In 2025, a tool that merely improves code, saves labor, and educates programmers is not enough. No project is going to get a green light unless it also welcomes our new robotic overlords. The problem is that large language models are trained on the corpus of existing text. And by definition, all of that code is old with respect to any newly added language feature. So there's a concern that models will continue to parrot old code, thereby entrenching that way of doing things. Models will get stuck in the past, speaking Go with an old-timey accent, like an actor in a black and white movie. So is this a real problem? Let's see how well current models do when asked to write Go code that could benefit from newer features. In other words, how modern is the dialect of Go spoken by an LLM? I did an experiment. For about 20 features of Go, I prompted a recent so-called thinking model to write a function that might use it. This example actually covers 2 features, split seek, the iterator version of split, and the min and max built-in functions. Here's the output from the model. It failed to use either of the newer features. What's more, it did this repeatedly, even after various prompts such as always use the newest available language and library features of Go. And it did this for all 20 of the features I tested. In fact, it is quite robustly stubborn in its refusal to use the new features, even though it can answer direct questions about them. In this example, I asked it to omit a trivial benchmark, knowing that there are two newer ways to write the loop. Even when told to use the newer features, it sticks to its guns. When the new feature is explicitly suggested, it defends its choice by saying that the old way is more common, which is true, even though it says the new way is better. And this was quite consistent across the 20 features that I tested. By the way, most of my LLM sessions seem to devolve into me pleading with the Turing machine, trying to get it to express remorse for the errors of its ways. So that was all using a faster and cheaper model. I also tried it with a more heavyweight model, which did somewhat better. A handful it got right off the bat. A few others it got when it was gently nudged in the right direction, or it produced comments explaining its choice to use the old way. Nonetheless, it still offered old-style code about half the time, as you can see here in the benchmark again. But when the fancier model got it wrong, it got it so wrong. It gives a misleading statement about how the benchmarking tool works, then it confidently states that range over int doesn't work, then it makes up a false history of Go, and then it dodges references to evidence with ever more complex and incorrect explanations. Why can I not stop falling into the same trap of hope followed by disappointment whenever I use an LLM? In short, there is a real problem here. And the solution to that problem is twofold. First, we need to fix the model. That means we need to improve the training data. And that's another way of saying, fix all the Go code in the world. The only way we can do that is by making you do that. And that means we need to give you tools that make it really easy. Second, we can patch up the model's inferences. Go's language server gopls already knows the structure of your Go project and offers its services to your editor. We recently made it also serve the Model Context Protocol, MCP, so that it can offer its services to your LLM-based agent. This will allow it to modernize the snippets of Go code that it emits on the fly. So both humans and AI agents can benefit from modernizers and produce better code. So that's the motivation of the problem. Now, how do we build a tool to automate these kinds of fixes? For the second part of the talk, I'm going to talk about the implementation of modernizers. In short, we use the Go analysis framework. This package, golang.org/x/tools/goanalysis, is the primary API. It defines the interface between analyzers, some people call them checkers or linters, and the driver programs that run them. This separation allows us to write a linter once, and then have it run anywhere in a sequence of different drivers. For example, it can run in govet in your CI system, and gotest also runs a subset of govet. It can run in standalone tools, which you can run across your entire module, or you could even run across the entire module mirror corpus of Go code, as we often do. It can run in code review tools. Google's large-scale analysis pipeline reports diagnostics as comments on your code review. And it runs in gopls, so you get real-time feedback in your editor, and you can fix mistakes right away. An analyzer is essentially a function that is called for each package in turn, in dependencies first order, analogous to the way a compiler builds up a set of packages starting at the bottom. This code shows the general skeleton of an analyzer. The run function is provided a pass, which holds the type syntax trees of the package and lots of other information. I'm not going to go into all the details. It's the job of the analyzer writer to fill in this loop with whatever they want. Most analyzers look at the syntax trees and report diagnostics. You can get as complicated as you want, but it's possible to write interesting interprocedural analyses in just a few dozen lines of code. So let's now build a simple analyzer that modernizes some old code. Here's a function that you've all used at some point, ioutil.readFile. It reads the entire contents of a file. In Go 1.16, we realized that the ioutil package was sort of a grab bag of things that really belonged in other places. And often, packages having the name util is a clue. So we moved all these functions out to those better places. Of course, because of the Go 1 compatibility guarantee, we had to keep the old functions working, so we couldn't delete them. Instead, we deprecated them and made them simply delegate to the new function os.readFile. Let's write a modernizer that finds calls to the deprecated function. Here it is. The run function looks at each file of the package, inspects the entire syntax tree looking for function calls, checks whether the callee of the function call has the right name, ioutil.readFile, and then it reports a diagnostic at the function call. So this is basically all it takes to write an analyzer. This diagnostic suggests that you use the newer function os.readFile. But But the analyzer needs to be incorporated within a driver program that will make the calls to the run function. So let's do that now. This one-line program is all it takes to turn an analyzer into a standalone command. We use a package called single checker, which produces a complete application that runs just one analyzer. And you just need to tell it which one to use. Here we use the read file analyzer. So now we can build an executable and run it on some code. By default, it reports one error on each line, like a compiler. And it has a bunch of standard flags for JSON output and such like. The -c flag causes it to display a few lines of context around the problem so you can see what's going on easily when you're looking on the shell. So this is enough to detect the problem and provide a diagnostic, but we can do better. Each diagnostic has the option to suggest one or more fixes, and a fix is basically a set of little textual patches to the code. This slide shows code to suggest a fix that rewrites the IO read file part of the function call by os.readfile. And this is just a toy example. A production-grade fix should also tweak the import declaration to ensure that we import the OS package. So now the single checker command not only reports the problem, it can fix it directly. Just run it with the fix flag, and it will quietly patch your code, and you can fix your entire project in one command. Here I've run it with the diff flag, so instead of modifying the files, it just shows you the change that it would have made. So that's the command line tool. But of course, the same analyzer can be run in other drivers too. If we add it to gopls, then your editor will start reporting calls to IOUtil read file and offering to fix them interactively. By the way, the analysis framework has been around for a while, and a lot of analyzers have been written for a variety of problems. gopls now has over 200 analyzers, a lot more than govet. And many of these come from Dominic Honeff's excellent static check suite. And we recently did some work with Dominic on some optimizations that mean that we can enable static check by default in gopls. So you should now be getting real-time feedback on a wide range of issues as you're editing. This is really all we need to know about the analysis framework. So then, what is a modernizer? Here's the definition we use. A modernizer is really just an analyzer with a few special properties. It suggests a fix. It's not enough just to flag the problem, it must fix it too. Second, the fix must use newer features of Go. And third, it must be safe to apply the fix with only cursory review. It must not introduce a bug. And this is an important point, and we'll come back to it in a moment. At the beginning of this year, we developed about 20 of these modernizers, as you can see here. And I want to give special thanks to Xie Yushen in Singapore, who made a lot of contributions. We also made the -fix flag work in the presence of merge conflicts, so you can now apply these fixes large number in your code base en masse. They were first released in gopls 18 in February, and you should have been seeing these diagnostics and suggested fixes in your editor for some time now. Along the way, we built some great infrastructure that unfortunately I'm not going to have time to present, even though I promised I would in my talk pitch. So what did we learn? Firstly, based on anecdotes, many users seem to like the improvements, although I think it can be hard for us to get an accurate picture. So let's do a quick poll. Raise your hand if you've seen this feature, these modernizers in your code. OK, about 20% maybe? OK, and now raise your hand if you applied the fix and were happy with the result. About 20%. OK, that's good. So the second thing we noticed is that even simple modernizers have a lot of bugs. Let's just take a look at one of the modernizers. It's one I wrote called range_int. We saw it earlier. It replaces a 3-clause for loop with just for range n, using the feature that AI confidently claims is not part of 122. It also gets rid of the loop index. In fact, it must get rid of the loop index if it isn't used by the body. Seems pretty simple, right? Wrong. I'm going to quickly show you 4 actual bugs in just this one of our 20 analyzers. Here's the first one, and it's very subtle. A range loop needn't declare the index variable. It can update the existing variable as it does with I here. However, when I is declared before the loop and used after the loop, the transformation changes the final value of I, introducing a serious latent bug. Fortunately, a single mysterious test failure and what seemed like a large but straightforward cleanup helped us catch this bug before it did us any harm. The second one is a very shallow bug. When I added logic to fix the previous bug, I forgot that there are more kinds of assignment than : and equals, and so I forgot about +=. And so this one slipped through the radar of the analyzer and caused it to mess up the code. At least this time, though, we got a compile error. The third bug is quite subtle. In the loop on the left, the type of I comes from 0, so it's int. The loop's bound is a float constant, but it's OK to compare with int since its value is an integer. But in the transformed code, the type of I comes from the constant n, so it's a float. So we've changed the type of I within the loop. If you're lucky, as in this case, it causes a compile error, so at least you can't overlook it. But if you're unlucky, it could just introduce a latent bug into your code. The fix is to introduce an explicit conversion when n doesn't have the same type as I. And here's the fourth bug. The loop on the left is intended to change its own limit, n, as it runs. This is admittedly quite subtle, but it does happen sometimes. So it may do fewer iterations than the original value of n. The transformed version reads the value of n once, and then ignores any changes to it. And this mistake is usually a subtle latent bug. The fix is to skip the transformation if the loop body might have side effects on the limit expression n. And that's actually a fairly involved computation. So that's the 4 bugs. We actually found 7 in this one analyzer, and there are 20 analyzers, and this is not even a particularly complicated analyzer. The point of all this, the reason I'm talking so much about bugs, is that it's really quite hard to get this logic right. Better infrastructure could certainly help, better support for testing, but you really have to think like a compiler writer and consider all the edge cases exhaustively. And that's just the correctness of the syntax manipulation. Source code is read by humans as well as computers. So unlike the output of a compiler, the output of a modernizer has to look good too. Comment handling has always been a weak part of our refactoring tools, something we plan to fix. But even then, there are always judgment calls. Does a comment refer to the previous line or to the following line? Should we delete a comment in a loop when we modernize away the loop, or keep it? It depends. In this example, the first comment is important and should be kept, but the second is trivial and should be deleted. There's really no good way to tell. And actually, this is an area where LLMs can make good guesses. But here's the thing. Since modernizers aren't fixing bugs, the benefit of each fix is pretty small. That means the costs, the risks of introducing a bug, or the effort required to review these changes must also be very small. Otherwise, it's just not worth it. So most users are going to apply all these changes without really looking for bugs. I'd initially been quite confident about modernizers, and even the prospect of democratizing the process of adding them so that anyone would be able to define a modernizer or other analyzer for their own APIs, and our framework would magically just pick them up and start dynamically and securely running them. But to me, the lesson of this experiment is that direct syntax manipulation takes a lot of effort to get right, even for experienced users. And by the way, it's not lost on me that while I'm fussing over correctness, the whole industry is diving headlong into vibe coding, and I do feel like a dinosaur. So this work on modernizers leads us to 2 questions. First, it's too easy to make mistakes that break the build, or much worse, introduce subtle bugs. How can we make these code transformations safer? Second, all these modernizers are bespoke algorithms tailored to specific features, and that's fine for the core language and standard library, which are used by everyone. But how can we enable you to modernize your own code base? I'm going to spend the remaining time of this talk discussing a different approach to modernizing that's inherently safer and is self-service. So let's recall our read file example from earlier. Notice that we keep the old function around, but its implementation just calls the new function. In effect, we're trying to have 2 names for the same function, and we express this as a wrapper function. There are many variations on this theme. For example, let's say your old function declares its parameters in a different order from the new function, like sub here. Or the new function has more parameters, and the old function passes a constant to one of them, like inf here. Or perhaps the old function is unnecessary since it's redundant with some other function in the new API, like neg here. In all of these cases, the desired behavior is that the user stops calling the deprecated function and instead does whatever the body of the deprecated function does. In other words, the user should inline the function call. So we built a tool that does this. To use it, you simply add a special comment //go::fix inline to the old function. Then you'll immediately notice in your editor, in the top box, that each call to the old function will trigger a diagnostic, saying that calls to oldmath.sub should be inlined. The diagnostic carries a fix that actually inlines the call. If you apply the fix, you end up with the code below. The use of the old package has disappeared, and the arguments to the call are now in the logical order. You can use this technique to do some quite large cleanups in your code bases in 3 steps. First, you build the new API that you want and express the old API in terms of it, like we did with old math. Then you add the go-fix inline directives and run the tool to clean up all the calls across your repo. And then finally, you delete the old API if you're able. Of course, it's not always so simple, but with a little creativity, you can express quite a lot of migrations this way. And in fact, within Google, the C++ team has cleaned up 2 million call sites using automation tools of this kind. In fact, the Google C++ team has a robot that automatically inlines all calls to annotated functions and sends out code changes to the code owners. So you can just add an annotation, and then it's like magic elves cleaned your code up during the night. So we hope to build the same thing for Go. So how does this work? It's based on a source-level inliner, which is a rather complex algorithm. The key insight is that all the semantic complexity and edge cases are dealt with systematically in the inliner, so there's no way for GoFix inline annotation to change the behavior of the program. For example, the naive way to inline a call to the sub function here is simply to replace y with the f call and x with the g call. But that can introduce subtle bugs if f and g have side effects, because it causes the call to g to occur first. Now, it's bad practice to rely on the order of effects within a single expression, but what we learned with modernizers is that the tool must be as correct as a compiler if we want people to blindly trust the integrity of their source to it. So the safe inline of this call is to insert a declaration of a new variable to hold the result of calling f before we evaluate g. And the source code changes can sometimes be quite fiddly. Order of effects is just one of a dozen very subtle considerations, and we don't have time to even name the others. The inliner is about 7,000 lines of very dense code, and I'm not going to go into the details. I have a whole talk on that for another day. But you can follow the link on this slide if you want to get a sense of what is involved. The GoFix feature I described is already deployed for interactive use in your IDE through gopls, and so you can try it out today in your own code base. For Go 126 or maybe 127, we're hoping to add this functionality to the GoFix command, making it easy to apply safe fixes en masse. There's already a GoFix subcommand. It does exist today, but it's really a kind of legacy of the early days of bootstrapping Go, so it's not used really very much. I'm going to briefly mention a couple of areas of ongoing work on the inliner. The first is comment handling. Comments are not recorded as part of Go's syntax tree, and consequently, the inliner, along with many other of our tools that do refactorings, will move subtrees around. They tend to misbehave with comments, either putting them in the wrong place or dropping them entirely. So we have some ideas for a systematic fix to this class of problems, but it's quite a project. The second is the problem of being too safe, which is a nice way, really, of saying it's unnecessarily pedantic. In the example of newmath.sub, if you know that the functions f and g in fact have no side effects, or at least no effect on each other, then the transformation to add bar y is just bad style, and you want to clean it up by hand. So we're working to make the inliner smarter in many ways to avoid bad style, but it's a bit like building an optimizing compiler. The job is never finished. So I'm going to wrap up now. I've presented two different kinds of modernization tools. First, modernizers, which are bespoke algorithms tailored to specific new features of the language and the library. They're fiddly, so we plan to add them only for the most important new features. And second, the auto-inliner, a more general tool by directive comments that you can add into your own code base. This approach is safer and open-ended and seems promising for other kinds of migrations. So please do share any ideas that you have with us for other code transformations that could be expressed in this paradigm. Both tools are already released for interactive use in gopls. And the batch commands, modernize and gofix, that I've shown on this slide, they're both temporary internal packages. It's not very satisfactory. But in due course, we will move them to their proper home in the gofix command in either Go 126 or 27. But please try them out and let us know what you think. Many thanks.